This video is about evaluating limits analytically. This word analytically here basically means algebraically. We're going to evaluate limits a few ways. Here they are. First is just using basic properties of limits, and then there are the factor, cancel, and rationalizing techniques. And then the last one, it's in your book, it's called the squeeze theorem. But you don't need to know that, which is nice. However, there are two special limits that we will talk about that you do need to memorize. We'll get there in due time. First way to evaluate limits is using what are called the properties of limits. These are described in your book. However, they're kind of cumbersome, and it's really easy to just explain it with an example. Hey, look, here's a limit. What we need to do is evaluate it, and guess what? We don't have to do any chart like that, none of that, blah, blah, blah. Instead, what we can do is plug it in and see what happens. All right, so let's plug it in. 4 times 2 squared plus 3. 2 squared is 4. 4 times 4 is 16. 16 plus 3 is 19. Great. Using properties of limits, all we have to do to evaluate a limit is plug in the x value. However, we cannot you cannot do this if the following happens. We can't break the rules of math. And so if you plug in your x value into the limit and you get something that divides by 0, that is not good, and we need to find another way of doing it. However, for any of the other ones where you can just plug in the x value, great. There's your answer. No more charts. Perfect. Let's take a look at what happens when this thing happens. The first thing you want to try if you get a problem where you're dividing by 0 is to try to do the factor cancel method. So here's a problem where that happens. Very clearly, we can see that if we plug in x equals -3, we get -3 plus 3, which is 0, and we get something over 0, which is bad. We don't want that. So we can use the fact that because this is a limit, remember that x does not equal -3, and that's going to allow us to do something very special. It allows us to factor the top of this equation. So if we factor the top, here's what we get. Very nice. We get x plus 3, x minus 2. 3 times -2 is -6, and 3 minus 2 is +1, in case you're wondering how I did that. But notice, if x is not equal to -3, that essentially means that these two can cancel and nothing bad will happen in terms of the rest of the fraction. So these two cancel, and then what we're left with is a new limit that is still equal to the old limit, and it's a lot easier to evaluate because now it's just x minus 2. And hey, we can plug this in, not have to worry about dividing by 0, and our answer is -5. So, first thing to try it is the factor cancel method. If you can factor the top or the bottom and make that division by 0 go away, great, do it. Other times, you might not be able to do that. Here's an example of a limit problem where you're not able to factor and cancel. Ooh, I don't like square roots either, but we have to deal with them somehow. Here's how you're going to deal with a problem with a square root. The technique is called rationalizing, and what we're going to do is we're going to multiply by 1 in a fancy form. Here's what it looks like. I simply rewrite the original limit. Notice that I put parentheses up here at the top. That's going to help me remember to distribute. And then I multiply by 1 in this really interesting form here. Right? Notice that it is 1 because it's the same thing on the top and bottom. Notice that the way I picked this special fraction is that I took the original thing, so the square root of x plus 1 and the 1, and I changed the negative sign to be a positive. This has a special name. It's called the conjugate. It's called the conjugate. And now we're going to multiply out the top. And if you notice, when we multiply out the top, it's going to be a difference of squares because we have something of the form a minus b times a plus b. And if you remember from algebra or whatever, that's going to give us a squared minus b squared, like that. So let's go ahead and multiply this out. Here's what we'll get. Limit as x approaches 0. Our first term is going to be squared x plus 1 times squared x plus 1, which is just x plus 1. Very nice. The cross term, if we do our FOIL, so first outer is going to be plus square root of x plus 1. Then we're going to have a minus square root of x plus 1. And then the last term is going to be the negative 1 times positive 1, which is simply a minus 1 there. And then on the bottom, we have x, the original x, and then times that fraction that was on the bottom. So we have x times, parentheses, square root of x plus 1, and then a plus 1 outside the square root. Let's go ahead and simplify this. Notice that I'm never dropping this x, or this limit symbol as I do this, because I still haven't plugged in 0 to evaluate it, so make sure that you don't drop the limit. Hey, as we cancel this, look what happens. We have a plus 1 and a minus 1. Those go away, and then this plus and this minus cancel out. And so all on top that we're left with is the x. So we have the limit of x divided by, on the bottom we have x and then the rest of the square root thing, keep it in blue, root x plus 1, and then a plus 1 at the end. Hey, almost done. Really quick, what's going to happen with these x's? They're going to cancel out, and you are still left with a 1 on top. Make sure that you don't forget that. But now, this is great, because now we can plug in 0, right? The square root of 0 plus 1 is just 1, and then we have so this here is 1, 1 plus 1 is 2, and then we have 1 divided by 2. So this limit eventually works out to be 1/2 using the rationalization technique. Again, what you're going to do is, if you have a square root, you're going to multiply by the conjugates, do some algebra, and what happens is that you should be able to cancel out that original x in the bottom to be able to substitute in that limit. Perfect. Now we get to talk about trig, everybody's favorite. Yay! The way that trig limits work is, guess what? As long as you don't divide by 0, you can plug in the number and you're good to go. So if we have the limit as x approaches 0 of cosine of x, easy. Plug in cosine of 0. The cosine of 0 is 1. You're done. Great. Now, there are some special trig limits that you do need to memorize. Here they are. The first one should look familiar because it was on your earlier classwork from section 1.2, and you did a t-chart with this. But basically, the limit as x approaches 0 of sine x over x is 1. The proof for this requires something called the squeeze theorem, but you don't need to know how that works. If you're interested, you could look it up in the book. It's kind of interesting. But just know that this limit is simply 1. And then the other one is this, that the limit as x approaches 0 of cosine x minus 1 over x equals 0. Again, this was also in that old assignment. This, I believe, was number 7 from section 1.2, and this one was number 8 from section 1.2. So if you want to go back and look at those t-charts to convince yourself that those limits are in fact 1 and 0, great, go ahead and do that. I'm going to do a quick example with this one just to see a variation on how this might show up on a test, quiz, AP exam, real life, etc. Here's a really deceptively easy problem, but it looks hard. And here's how we're going to do this. We have sine of 4x, and I'm not going to worry about any double angle formulas or anything stupid like that. All we're going to do is we're going to try to make the bottom match the top part that's inside the sine. Well, the sine has a 4x, so what we're going to have to do is we're going to have to put a 4 on the bottom to be with that x right there. Well, if we multiply by 4 on the bottom, we have to keep the fraction the same, so we're multiplying by 1 in a very special form, like this. And if I rewrite our limit, we'll have the limit as x approaches 0 of 4, the green 4, sine of 4x from the original problem, divided by the green 4, and then the x from the original problem. And here's how I want to group this. Notice that you have a 4x and a 4x, and you have this right there, and x is going to 0, which means that the stuff inside the sine is going to 0, and the stuff on the bottom is going to 0, which means by this last limit here, which means by this limit here, that this whole thing in blue is just going to go to 1. Perfect. So our limit, our final limit, is equal to 1 times, wait, don't forget that green 4. It's still there. So our final limit is simply equal to 4. So if this kind of problem shows up again, just remember, multiply the bottom to match whatever is inside that sign, and then that top part will stay with you till the end of the problem. Feel free to ask questions in class about this. It is a little bit tricky.